Okay, we're now going to consider the topic of critical transitions, which describes a situation where a system reaches some kind of threshold or tipping point where there's a sudden change in its behavior. So a war breaks out, or rioting erupts on the streets, or the economy crashes, or there's a shift in people's attitudes from, for example, homosexuality is wrong to homosexuality is fine. Now, when I referred to wars breaking out earlier in the course, someone commented, wars don't just break out, they are made to happen by the bankers or what have you, which may be true, but nevertheless, there's some kind of transition when war seems to become the answer. And it's those kinds of transition that we want to model and understand. Now, when there is such a change in behavior, it's as though the system has two fixed points, peace and war, or booming and depression, and it switches from one fixed point to the other. So let's review our understanding of fixed points. Okay, so here is the system described by some variable x, so it's a one-dimensional system, and here is the function which I've written as f of x, which describes its rate of change. So f of x equals x dot. X dot is just some function of x, f of x. And what we saw is that when the slope going through the axis, so when x dot is 0, when the slope is negative, it means that the fixed point here is an attracting fixed point, because below the fixed point the rate of change is positive, so it moves up, and above the fixed point the rate of change is negative, so it moves back towards the fixed point. So it's an attracting fixed point. So we can say that when df by dx is less than 0, the slope of the function f is less than 0, then that implies an attracting fixed point. And we'll now start calling this a stable fixed point. So it's stable because if the system is at that fixed point and then some kind of disturbance knocks it away from the fixed point, it will move back towards it. So it's stable. It tends to stay where it is. And then we said that when the slope going through the fixed point is positive, then it's a repelling fixed point. Things tend to move away from it. Below, it has a negative rate of change, so it moves further away, and above it has positive, so it moves further away. So we can say that when df by dx is positive, greater than 0, it's a repelling fixed point, or we'll call it unstable. So that if it's at that fixed point and there's a slight disturbance, then instead of returning, it will just fall over into some other state or head off to infinity. And then we also saw that we can have this intermediate situation where in this case it just touches the axis. So here we've got df by dx equals 0. It's just touching the slope is 0 at that point. And we said in this situation it's seems to be stable or attracting from below, because from below the slope, the rate of change is positive, so it will move towards it. But above it's also positive, so if it's above it will move away. So we can call this something like semi-stable. Before we called it the saddle point. And we represent stable fixed points by a solid dot or circle and an unstable fixed point by a hollow circle dot. So this semi-stable one, we can have it half and half. Now here we've got it touching from above. It could also, of course, come from below and just touch, in which case it would be semi-stable, but switch the other way around. It would be repelling below and attracting above. And then we can have also other situations. We can have something like that, where it's like this, just touches, but instead of then going up again, it comes to a zero slope, but then it bends the other way and goes off in the negative direction. And here then we have df by dx equals 0, but this would actually be kind of stable, because below that fixed point, so I can put it as a solid dot, below that fixed point this x dot is positive, so it will move towards it, and above the fixed point x dot is negative, so it will move back towards it again. But because the slope is 0 here, and just beyond it on either side the slope is very close to 0, it means the rate of change is very close to 0 around the fixed point. So although it will move back very slowly. The rate of change is very slow. So it is stable, but it's very slow at returning to its equilibrium position. And to distinguish between these situations, we would need to consider the second rate of change, d2f by dx squared. How is, df by dx is the slope of this line. How is the slope of the line changing? That's d2f by dx squared. Well, here at the fixed point, the slope is increasing. So d2f by dx squared is positive. Whereas here at the that fixed point, the slope is becoming increasingly negative. So d2f by dx squared is negative. So to distinguish these situations, we need to consider what's happening in the second rate of change, and that will tell us whether it's semi-stable or stable, but with a very slow tendency to return. So we're going to model critical transitions in terms of fixed points. So let's start with the system we had earlier, where x dot equals x into 1 minus x. And we'll draw the graph we had of that. Okay, so there's the graph we had before. We have a system with described by the variable x, which is along here, and on the vertical axis is x dot, its rate of change. So this is the function f of x that describes the rate of change. So in this case, the function of x that we're studying is x into 1 minus x. And this gave us two fixed points, one here at 0 and one at 1. So when x is 0, this is 0. When x equals 1, this is 0. And we also know that this is an unstable fixed point because the slope through there is positive, and this is a stable fixed point because the slope is negative. So I've shown a hollow for a point there and a solid one there. Now we said that the idea of a transition is of a switching from one fixed point to the other. And we've got two fixed points here, but this one being an unstable fixed point isn't really what we want. So when there's a switching, it's between two stable states of the system. So it's in the state of peace, and that's fairly stable for a while, and then it switches to war and it remains in war. It's a stable fixed point. It doesn't go into war and then immediately flick back away from that, because war is an unstable state. War becomes the new stable state. So what we want in this diagram then is another stable fixed point. So we certainly want to add another fixed point to the diagram. How can we do that? Well, that's very straightforward, because we know that if we add another bracket here, something like a minus x, then when x equals a, this will again be 0. X dot will be 0, because a minus x will be 0, so it will be something multiplied by 0. So if we add just another bracket to this, then we're going to add a fixed point at x equals a. And what I'm going to do is, just to keep this diagram nice and symmetrical, is add a fixed point at -1, and we want it to be a stable fixed point, so we want a negative slope. So we want something coming in like that, and then we can just join that up. So we're going to now have a stable fixed point here, a stable fixed point there, and an unstable fixed point between them. And you can see that if you have two stable fixed points, you will have to have an unstable fixed point between them, because if you're going to cross from positive to negative of side of this axis here, and then you're going to cross from positive to negative here, at some stage in between you've got to go from negative back to positive, so you can cross back down the same way again. So if we're going to have -1 for a, well, what we can do here is write this as 1 plus x. So in this case, when x is -1, this will be 0. So we've got our two fixed points, and if the system is anywhere on this side of the x dot axis, it will move towards this one. It's, if we show the arrows of the phase portrait, here it's moving towards that from below, and also towards it from above. Here it's moving towards that from above and below. So we say that this has a basin of attraction from here to -infinity. Anywhere that's between 0 and -infinity is going to be attracted to that one. That's its basin of attraction. And then similarly, this one has a basin of attraction from 0 up to +infinity. And this is on the fence. Now, in our system, it might be at a fixed point, but there can also be disturbances to the system. So it might be a new technology comes along that, you know, changes the economic picture, or it might be that there's a natural disaster. So, you know, if we're here in a booming economy, a natural disaster kind of will make the economy decline a bit. Now, if it doesn't make it decline very much, the natural disaster will just shift it somewhere still within the basin of attraction, and then it will come back to where it was. So you'll be back into booming. But if the natural disaster is big enough that it shifts it past this unstable point into the basin of attraction of this fixed point, then the system will switch to this negative fixed point. So we can imagine that the system is hovering around its fixed points, but subject to disturbances. And if those disturbances are small enough, at least compared to the size of the basin of attraction, then it will remain where it is. But if the disturbance is big enough, then it can shift it past this unstable point and into the basin of attraction of the other one, and that's when the system will switch. So switching can occur because of disturbances, but we're now going to take a look at how switching can occur because of structural changes in the system. Okay, so I've written up here our equation again for x dot. This is the system we're looking at, x into 1 minus x into 1 plus x, with its fixed points at +1, 0 and -1. And while we're looking at this, we might note that 1 minus x into 1 plus x could be written as 1 minus x squared. 1 minus x times 1 plus x is difference of two squares, 1 minus x squared. And then if we're multiplying that by x, that's going to be x times 1 minus x squared. So that's just x minus x cubed. So we could write this function for x dot as just x minus x cubed, but writing it out like this, highlights the fixed points at 0, +1 and -1. So it's kind of more intuitive that way what it means than looking at it like that. But nevertheless, that's another way of writing it that you might sometimes see in discussions of this equation and its properties. Now, what I'm going to do is take the liberty of adding a constant to this, c. So in this original configuration that we were looking at, c equals 0. And we had our two fixed points, two stable points at -1 and +1, which are shown there. But now let's think about what happens if we change the value of c. And I'm going to just talk through this purely in terms of the mathematics in an abstract way, just to see what's going on, just from the mathematical point of view. And then we'll talk about a real world scenario to try and make sense of this and see how that could apply in real life. I think it's going to be helpful if we just look at the pictures first and see what's going on. So, I've added this constant c, and what happens if c is not 0 but is got some positive value? Well, what that will do is it just adds c to everything. So it's just going to shift the whole graph up by the value c here. So I've shown this dotted line, everything's been shifted up. So it's now symmetrical around that dotted line. And I'm going to label these points here, the fixed points. That's A, B and C. So A and C are the two stable ones, B the unstable. And we can see here that now if we label our fixed points, A is there, B is here and C is here. What's happened is that A has shifted slightly to the right as this has moved up, and B has shifted to the left. It's no longer at 0. It crosses the axis up here now. So where it crosses this x-axis, perhaps I should have labelled these, that's x and x dot, the same for the others. It's no longer at the 0 on the x-axis. So what that means is that the basin of attraction for the fixed point at A has decreased, while that for the fixed point at C has increased. So that means that if you're at A, disturbances are now more likely to be able to shift you out of your basin of attraction to C. So with this addition of this constant C, it's kind of made A less stable than it was before. It's at least less stable in response to disturbances. It can be knocked out of its basin of attraction by smaller disturbances than before. And then let's suppose we increase C further. Now the graph just touches the x-axis here. So what's happened is that A and B have kind of come together. And so this is a semi-stable point now, a kind of amalgam of the stable point at A and the unstable one at B. So this is, very vulnerable now to disturbance, because yes, if the disturbance takes it into the negative, then it will come back towards it. But any disturbance that moves it in the positive direction will immediately put it in the basin of attraction of C, and so it will go to this fixed point. And then supposing the constant C increases further, shifting the graph up so much that it now doesn't even touch the x-axis here, well, we've lost the A and B fixed points, and we've only got C, the fixed point C left. So in this case, the system will have to move to C. So as we go from there, increasing C to here, if we start at A, we're becoming sort of more and more vulnerable, and then we're forced to C. So the switch definitely occurs. So now let's think about a real-world scenario that this might describe. So let's think of it in terms of an authoritarian country where X measures the level of protest, street protest. So if we think about this, what this is telling us is that when we're down here with a low level of protest in the country, then the police are rather inactive. So there's not much protest. They prefer to stay in the warmth of the police station eating donuts. So that means that there aren't many police around. So the few sort of troublemakers can come out on the streets and cause protest. So there's a positive rate of increase of the level of protest. So protest is generally pretty low, but because there's very few police around, the protesters, the troublemakers can come out on the streets and cause some sort of protest. But when they do, the police get to hear of it, and then their boss sends them out on patrol to deal with it. So there's a heavy police presence and just a few troublemakers. So those few troublemakers, slip into the shadows and go home. So that puts us at this fixed point here. When the police go back to the police station, the troublemakers come out on the streets. But when the police come out in force, the troublemakers go home. So there's kind of a low level of protest that is just what the police will tolerate. If it gets much above that, then they'll come down hard on it. But at this fixed point there, they can overlook a few occasional troublemakers. But then let's suppose that for some reason mass protests have broken out. Then we're somewhere up here. This means now, though, that the police are overwhelmed. There's hundreds of thousands of people on the streets and only, a few thousand police to deal with them. So the police are in a sort of damage limitation stage. They can't really bring the protests under control. So seeing that, other people are prepared to join the protests because they feel safe. There's safety in numbers. So more and more people will come out on the streets. And so the amount of protests will tend to increase. But then if it goes past a certain point, people see, well, there's so many people on the street now, I'm not really needed. I mean, the point is being made. I can go home, and have my lunch or go to work or do other tasks that I've got to do. So, so if the number of people on the streets gets too large, some of the people start melting away and going home. So it falls back again. So there's a kind of stable equilibrium up here as well, a stable fixed point that if it goes below, people will come out on the streets. If it goes above, people will tend to go home. And in between, there's this kind of unstable fixed point where there's enough people on the streets that the police can't exactly control it, but it's not enough that people feel really safe. Well, it can then go either way. If more people come on the streets, then the police are overwhelmed, and then that encourages everybody else to come out. But if a few people drift away, then the police are starting to outnumber the protesters, and it will fall back to this point A, the low level of protest. So there are those two basins of attraction. And now consider what happens then, though, if C increases. So an increase in C could be something that makes people more angry, more prepared to protest. So let's say there's the dictator introduces a new tax on people. So that makes people, more angry. So more prepared to protest. So it shifts the curve up. So what we now have is that this lower fixed point has moved up a bit to the direction of, remember, X represents the level of protest, to a higher level of protest. So, but only a little bit. But nevertheless, the level of protest has increased. And then some other provocation happens. Let's say the dictator imprisons a popular opposition figure, which upsets people even more. So their anger level is raised. And now this low-level protest has become semi-stable now. And then another provocation occurs. Let's say, a protester is killed by a rubber bullet or something, and the anger level increases. Now people are so enraged that we switch to mass protests. And from the perspective of the regime looking at this, it can think that things are going okay because it's raised the taxes, and it produced a little bit more protest, but nothing too much to worry about. The police still have it under control. It's not moving beyond that low level of protest. And then, they've imprisoned that opposition figure, and they can see, well, again, the level of protest has increased a bit, but they can feel that they're still, the country can still take it. It's not, the level of protest is not really increasing that much. But then that final provocation causes it suddenly to switch. And so from their perspective, they're thinking, as we provoke people more, that protest increases, but it's manageable. But then at this point, just a little bit more lifts this off the axis, and suddenly the country will switch to mass demonstrations, and they'll sort of wonder why. Well, it was only a small extra provocation, but it was a straw that broke the camel's back, and or in other words, lifted the fixed point off the axis and left us with only one option at this high fixed point of mass protest. And what's more, then the regime can think, oh well, we'll just make a few concessions to get people back. So they might make a concession and perhaps lower the graph again, but we're now at this fixed point. So there's no reason for the country to leave that fixed point. The mass protests will continue. And we still go back to here. The mass protests will continue because we're around here. We're in this basin of attraction now. And even we go back all the way to the beginning, we switched to C, so we're at C. And what the dictatorship would have to do would be to have to give so many concessions that eventually they get to somewhere like this, and they've caused that mass protest fixed point to disappear, and then finally it will switch back. But this is, a negative C, a large negative C. So they have to make massive concessions to get it back. Well, they probably never will achieve it. So the only thing that will get the curve back to this is something like the dictator resigns and flees the country. So the point is then that you can switch to this higher fixed point, and getting back again is not just a case of reversing it. You have to go much further back in order to get back to square one. So this is known as hysteresis, where you make a change in that direction, and the thing to undo that change takes a lot more effort than it required to produce that change. And we can kind of represent that with a graph where we show how the fixed points depend on the value of this constant c in this equation. So it's slightly confusing because I'm going to put x on the y-axis now, if you like. I'm going to put x on the vertical axis and against the constant c here. So we're going to plot where the fixed points are. In x as a function of c. Well, when c was 0, we had them at +1 and -1, if you recall. So when c is 0 here, they were at +1 and -1. And this was the fixed point c, and this was the fixed point a. And as we can see then, as c increases, a starts to move towards 0. It moves in the it's in the negative axis, a part of the graph, but it's moving in a positive direction, so it's increasing towards 0. So a is going up here. And we also see that c is going up as well. And as c keeps increasing, c will keep going up. And it will, go up indefinitely, really, because this can go as high as it likes, but c will just keep shifting as that moves up in that direction. And what about if we go negative? Well, if we go the opposite way, as we can see here, where I've got a negative c, a is now moving in that direction. So it's going to become more and more negative. And c will also, from here, tend to become negative. So it's going to look like that, something like that. But now let's also go back to thinking about a. So as c was increasing, a was increasing, becoming more positive, closer to x equals 0 here. But at a certain point, when c reached a certain point, a disappeared. So a will not keep increasing forever. At this value of c, which I can call, let's say, c1, c1, a, that fixed point disappears. So it comes to an end. And the same applies then to the fixed point c in the other direction. When we shift it down, c eventually disappears, as it's disappeared here. So there's a c2, value of c2, where c disappears. So on this graph we can look at the same kind of thing I talked about here, just in a different way. So that if we're at the fixed point A and c is increasing, we're moving up along here, so the fixed point at A is increasing. Then we reach a point where A just disappears, and at that point we're forced to switch to this fixed point. And then as C increases, we'll carry on along there. Or if this is a point where the government sees a mass protest and think it's going to give concessions to get the mass protest back to disappear and people go back home. It's now on this part of the graph though, so it's decreasing C, but it's still up here, and it has to decrease C all the way to here, and then it will fall back to A. So this is what is known as hysteresis. So we've seen that in the case of protest, but it could apply to other systems with critical transitions. It's like if the economy crashes due to some reason, just reversing that reason won't put the economy back where it was. You're going to have to do, take massive steps to get it to switch back again because of this hysteresis. Once you've switched, you've reached the limit, you switch to that one, you've got to come a long way back to get back to where you were. Similarly with a war, once war has broken out and unleashed the bloodlust, then it takes an awful lot to get it back to a situation of peace. Hysteresis. And this equation, x minus x cubed, or that, is the simplest equation you can have that will show this kind of behavior with these two fixed points, two stable fixed points, and this hysteresis. But you could clearly add more terms to this to create more fixed points and get complicated situations. But yeah, so that's a good model of the critical transitions. And now, if you are the government and you sort of realise this, that you can get yourself in the position of losing your stable fixed point of low protest, you might want to have some way of telling where you are. How close are we to this point, or this point here? How close have we got? We're pushing the population with all these taxes and cracking down on opposition. Are we here though? Can we do a bit more, or are we getting close to this tipping point where we'll suddenly end up having a big problem on our hands? So you want some kind of early warning of it, and we'll now consider how you can do that. Okay, I've drawn two fixed points here, and we can see that they're stable fixed points because the slope of the graph going through them is negative. But here it's very steep, whereas there it's rather shallow. And at both fixed points, if the system is disturbed away from the fixed point, it will move back towards it. But it will do so at different rates, because here, if the system is moved a short way away from it, x dot is very large and negative because of this steep slope. X dot here is very large and negative, so it will be moving back quickly, very fast towards the fixed point. Whereas here, if it's disturbed the same sort of distance away from the fixed point, the value of x dot, because this is a shallow slope, is quite small. So it will only be moving slowly back towards the fixed point. So how fast the system returns to the stable position depends upon the slope of the graph as it goes through the fixed point. And if we look at the system that we've been considering with we had a fixed point A, B, and there was a C over there. Well, this was our x dot axis, I suppose. That's x. So we had that situation. What you can notice is that as the slope here if it's that there, is decreasing and it's 0 at the bottom. So that as A shifts, as the system shifts up, the slope at the point where it's crossing, or you know, where the fixed point is getting shallower and shallower until it's 0. So because the slope decreases to the minimum here, as that C parameter shifts the thing up, the slope of where the fixed point is decreasing till it reaches 0. So because it's decreasing, the speed at which it will move back towards the fixed point is going to become smaller and smaller. And so for a given disturbance, it will take a longer time for the system to return to equilibrium. And that is known as critical slowing down. As we get closer and closer to the critical point, which is here, where beyond that we will switch to the other stable point, the system's response will become slower and slower at the lower fixed point. It will, you know, as I say, take a longer time to return to equilibrium. That is critical slowing down. And we can look at that mathematically, which we'll do briefly. Okay, so here we are again with our basic scenario. So we've got the variable x along there, and this shows x dot, which is some function of f of x. And here's our fixed point, and it's a stable fixed point because the slope is negative going through it. And I'll call the value of x at this point xe for equilibrium. And what we're going to do is consider that we've made a small displacement away from the fixed point, a small disturbance, if you like, represented by epsilon, the Greek letter epsilon, Greek letter E, small epsilon. So we've been disturbed a little bit away from the fixed point, and we want to know how fast we're going to be moving back towards it. So we're interested in dx by dt. How fast this will return, the rate of change of x. Well, we know that since this is x dot is f of x, we know that then d by dt of x, which is the x value here, is just xe plus epsilon, equals f of x. This shows us what x dot is, dx by dt. So it's equal to the function at x, which is xe plus epsilon. And if we take this, d by dt of xe plus epsilon equals d by dt of xe plus d by dt of epsilon. And xe is just a constant value, it's just where the fixed point is, it's not changing. We've moved away from the fixed point and we're going to be moving back towards it, but the fixed point itself remains where it is. So xe is constant, it's not changing with respect to time. So this just equals d epsilon by dt. So the rate of change of x is the same as the rate of change of epsilon. And as for this, well, we know that by definition df by dx is equal to the value of a function at x plus dx minus the value at x divided by dx. That's the change in the function divided by the change in x. That's the definition of df by dx. So that tells us that, just rearranging a bit, we can say that f of x plus dx is equal to f of x plus df by dx times dx. I mean, we can see it another way because the dx's cancel, and then so that says the function at x plus dx is the function at x plus the change in the value of the function df. So in here we've got this is for an infinitesimal dx, but we could this isn't a infinitesimal, but it's a small change in x. So we could say, you know, for this it's approximately going to be the case that that f at x plus a small change delta x is f of x plus df by dx times the small change in x. So long as the change is small enough, this will apply. It won't be fully apply because the slope is changing. You know, this is sloping away like that. So that because of the change in the slope over that distance, we can't assume the df by dx is a constant value. But if it's small enough, the slope doesn't really change that much over that distance. So this approximately applies. So in our case, we've got for x we've got xe, and for delta x we've got epsilon. So we can write this as the value of f at xe plus df by dx times our delta x, which is epsilon. And df by dx is just the slope of this line, and it is just some value. It's the slope as it's going through the fixed point. So we could we'll call that just a constant value, lambda, the Greek letter lambda, Greek letter L. Only it's a negative slope, so let's just make that clear by calling it minus lambda. So that is equal to f at xe minus lambda times epsilon. Now, what's f of xe? Well, because this is a fixed point, x dot at the fixed point is negative by is 0 by definition. X dot is f of x up here, and at xe the line is going through the x-axis, so at xe the value of this graph is 0. So f of xe is 0. So that is just minus lambda epsilon. So we have on this side, this is the same as d epsilon by dt, and on this side it's equal to minus lambda epsilon, where lambda is the slope of the graph, df by dx. And so putting these together again, we've got d epsilon by dt equals minus lambda epsilon. And that's a straightforward differential equation which we should know how to solve from our the calculus part of the course. So it's just an exponential function. It's like dx by dt is proportional to x, so it's got an exponential solution. So we will have epsilon is proportional to e to the minus lambda t. Differentiate that with respect to t, and you'll just bring the minus lambda down in front. So you've got d epsilon by dt equals minus lambda times itself. So what that says is that if the system is disturbed a distance epsilon away from the fixed point, then it will the disturbance will decay back towards the fixed point at an exponential rate, where the speed depends on this lambda, which is just the slope. So that's really just formalizing in mathematical terms what we said intuitively earlier, that the steeper the slope, the faster the system will move back towards the equilibrium point. And that's because it depends in this way. It's an exponential decay determined by, or the rate is determined by lambda. The larger lambda, the faster this will decay. We can also see that if the f by dx is positive, if we had a plus lambda in there, then it would say that if you moved away a disturbance, it would grow exponentially, because you'd have a positive lambda. It would grow and just keep moving away exponentially. So that's what would make it an unstable point if lambda were positive. Obviously, it would only move away exponentially over a short distance, because we're assuming the disturbance is small. So once the disturbance has become large, it wouldn't really be obeying that equation anymore. But for small disturbances, that applies. So this is critical slowing down, telling us that as lambda decreases, as we move towards a critical point where we're getting towards this minimum point where the slope is 0, as this is moving up, then lambda is getting towards 0, then it will be getting slower and slower in terms of the decay of the disturbances. And so if you're a regime intimidating your population and imposing taxes and creating other doing other things to anger your population, you want to monitor how quickly protests die away when they break out in response to each of these aggravations. If they decay quickly, then you can say, we can aggravate more, we've still got a lot to play with. But if they're decaying slowly, then it implies you're getting to a critical point, which is perhaps common sense anyway. So yes, all our mathematics leads us back to common sense, which perhaps relates to something I said in an earlier lecture about how the principles on which the cosmos operates and on which history and society operate are really quite simple, and all the mathematics is about uncovering that simplicity, which some people are able to perceive directly through their own intuition. But that doesn't mean that this is just trivial, because our mathematical analysis has led us to understand what the variables are, what the things we should be looking at are. It also reveals the connections between things like outbreaks of political unrest and crashes in the economy. And it also suggests how we can quantify our understanding, by measuring the time for disturbances from equilibrium to die away. And now the propensity for critical transitions may itself be something that varies between situations. So, for example, in democratic countries, changes in the political regime, in the political complexion of the country, can happen peacefully and in a smooth sort of way through elections and by-elections. So the country may shift to sometimes more progressive attitudes, and then sometimes to more conservative attitudes, and go back and forth. But it happens relatively smoothly. There's no violent revolutions involved. Whereas in more authoritarian countries, a particular regime remains in power for decades, and then there's an abrupt collapse of that regime, and some new political order is put in place. So in the more democratic societies, we don't really see critical transitions, but in more authoritarian ones, we do see critical transitions. So this propensity for critical transitions is itself a variable. And what I'm going to do now is look at an extension of this model that tries to capture that idea. So we had our equation, which was x dot equals x into 1 minus x into 1 plus x. And I said that that could be written just as x minus x cubed if we multiply out the brackets. And what we're going to do is stick a parameter a, in front of this x. So it becomes x dot equals ax minus x cubed. And I'm going to plot what we get for different values of a. Okay, so here are three plots of this equation for different values of a less than 0, a equals 0, and a greater than 0. So let's have a look at a less than 0 for a start. So if a is less than 0, and when x is positive, if a is negative, then this will be negative, and minus x cubed will be negative. So when x is positive, the value of this function is always negative. And as x becomes large, this, the x cubed term becomes much larger than the ax term. So this just becomes like x cubed. And then when x is negative, if a is negative, this will be a negative times a negative, so that will be positive. And if x is negative, x cubed is negative, and that's a minus a negative number, so that's positive as well. So on this side, it's always positive. So that's what we're seeing, and it becomes like x cubed when x is large. So we see this kind of shape. And then when a equals 0, well, the first term here is disappears, and we've just got x dot equals minus x cubed, and that's what this graph is, minus x cubed. And it's like this, but the only difference is that it becomes flat at the origin, and briefly goes to a slope of 0, whereas this one it will be have a positive slope, a negative slope, but a finite slope as it goes through the origin. And then if a is greater than 0, and we've been seeing the example when a equals 1, we've been considering, but in general, if a is greater than 0, we get something like this going down, up and down again. And that's because when a is positive, then this is a positive value minus x cubed. So if a is if x is small, then ax is larger than x cubed, and so we can get that kind of we can get a positive part of the graph. But then when x becomes large enough, the x cubed dominates the ax and is much larger than it, so it's negligible, so it's minus x cubed again. And conversely, on the other side, when if a is positive, then and the x is negative, a positive times a negative, that's going to be negative, so that will be positive because x is negative, so that's minus a negative number. But that's positive. That's so that is positive, did I say, minus a negative number, but this is negative. So there is a little bit when x is small that is below the graph is negative, but then as x becomes large and negative, the x cubed dominates, so minus a negative number, it will be positive. So we get these three different situations. And now let's have a look at the fixed points. Well, we know this one is what we've been looking at. There's a stable fixed point there and there, and an unstable fixed point between them. And what about here? Well, the slope is negative as it goes through the x dot equals 0 point, so that's a stable fixed point. And there's only one fixed point. And here, this is a fixed point, and it's also well stable, but we saw earlier how because the slope goes to 0, it will be very slow in coming back to the equilibrium around there, because with a almost 0 slope, the rate of change is almost 0, so it's very slow returning to the equilibrium after a disturbance. So as A varies, we have we go from a situation with one fixed point and a stable fixed point to a situation with two stable fixed points on either side of an unstable fixed point. And now let's add back in our constant c that we had before. So we'll have x dot equals c plus ax minus x cubed. What we'll do is, same as we did before, we will plot how the fixed point in x changes as c changes. So in this situation, when c is 0, which is what we've got here, because that's just ax minus x cubed, so c is 0. So we've got a fixed point at the origin 0. So the fixed point is when x equals 0. And then as c increases, so we'll be shifting this graph up. The draw that well. As we shift the graph up, will be the point where the graph intersects the x-axis will be shifting to the right. So we'll be getting a fixed point more towards the right in the positive x. So it will be tending to increase. And opposite, if we shift the graph down, the fixed point will be moving to the left into the negative. So how the fixed point will vary will look something like that as c changes, as we shift the graph up and down. Then we'll skip over that because it's pretty much the same thing as this. Just look a different shape, but we'll go over to this one. Well, we've already seen it, so let's just remind ourselves, we'll just draw it. We get two fixed points, and we saw that if we call that C and that A, we've got these two branches of fixed points. The fixed point A, which will be shifting in the positive direction. Well, both of them will shift in the positive direction as we increase C. But A will eventually collide with the unstable fixed point and disappear at this point. And similarly, this fixed point C, if it's shifted up, that will always exist. So that will go as C increases, the fixed point there will always increase. That line will continue to infinity. But as we shift it down, eventually we'll reach the top there, brought that down, and it will disappear at a certain value of C that is negative when it's shifted below the axis. And we can kind of draw a sort of dotted line between them, representing that's the unstable fixed point. That's where the unstable fixed point is. Should go through the origin there. And what we can do now is kind of summarize both these things in one three-dimensional graph where we'll plot where the fixed points are as both A and C vary. So it will look something like this. Okay, so this is a three-dimensional graph which puts together that and that. So we've got A, sort of coming out at us here, and C varying there, and then this shows where the fixed points are. So if we have low values of A less than 0, we've got these situations, we've got something like that. It's just one fixed point varying smoothly, so, and that's down here. But if we have larger values of A greater than 0, then we've got something that looks like that. If we're looking at edge on, as C changes, we've got this doubling back on itself. So that's somewhere like here, where it's doubling back and on itself. So what we've got is this sort of shape that's like got a fold in it. And this is known as the cusp catastrophe. And catastrophe doesn't really mean you know, a disaster. It's just a technical word in mathematics to describe this things that fold like this. And in fact, it is one type of catastrophe that you can get where there are multiple fixed points. And the discipline of catastrophe theory within mathematics is devoted to looking at the different other kinds of shapes you can get. And there are 7 different catastrophes in all, so you can get more complex behaviors than just this. But this example of the cusp catastrophe has been adopted by some people to describe socio-historical phenomena, and because it's kind of the simplest one to understand. I'm not sure, I haven't seen anybody use more elaborate catastrophes, but perhaps they have, to think about socio-historical systems. Catastrophe theory was quite popular in the 1970s, and there was a book brought out in the 80s called Transformations, Mathematical Approaches to Culture Change by well, one of the editors was Colin Renfrew, a professor of archaeology at Cambridge, and it was a collection of papers using mathematics to understand culture change, but several of them were looking at the applications of catastrophe theory. And there's another way we can sort of draw this. If we imagine looking down on this, then we don't need to sort of try and draw 3-dimensional charts. We can just have a 2-dimensional one. So if you think of looking down on this, so we just look at A and C. So we have A varying here. So we've got 0, say -1 there and +1, and C varying in this direction. So C can vary from 0, +1 to -1, let's say. Doesn't really matter whether it's +1 or -1, but just negative and positive. The exact values will depend on the exact values of the parameters. So yeah, so A is increasing in that direction. So if we imagine we're looking down on this, so C there is C there, and A coming out here is A there. So we're kind of looking down here, and that direction is A. So we're looking along A. So what we find then is that if I just draw a grid there, that's the 0. It's from the 0 here that it splits up. So from here we'll have this region. There we have 2 fixed points, 2 stable fixed points. So in that region we can have critical transitions. So that is the region where we've got this fold in the graph. So for values of C and A in here, there won't be any critical transitions. It will just be smooth variation. So this is like in our democracies, where if we think of this as involving changes in the political complexion of the country, there won't be any sudden switches. But so A is a measure of whether we're democratic, which is where we don't, as C varies, what it might be something like, say, the state of the economy that causes people to switch from more progressive to more conservative attitudes. In a low authoritarian country, there's no possibility of critical transitions. It will just, as the economy varies, people will smoothly go back and forth between these attitudes. But in a more authoritarian country, it will happen as the economy changes. The transitions will occur more violently. There will be a switch between two stable fixed points, so you know, as the economy is worsening in a left-wing or progressive regime, people may switch to be more right-wing. But if it's in a right-wing regime and the economy is worsening, they may switch to be towards a more left-wing point of view. But there's this sudden switching. The old regime tries to hold on and hold on and hold on, and then it suddenly collapses as it goes past the critical point here, and it will switch from one to the other. So let's summarize the ideas coming out of this model. So the first one is the idea of stable fixed points, or attractors. So this is the idea that a system can have two different states that are both stable. So it might be peace and war, or economic boom and economic depression. Both states are possible, though it will only be in one or the other. And then there's the idea of critical transitions. Which refers to the idea of a sudden switching between states. So if we've got these two alternative states, it's in one, it can then switch to the other. So rather than a smooth change, it will go from the one stable possibility to the other stable possibility in a jump, critical transition. And then there's the idea of attractor basins. So this is saying that for certain states of the system, it will tend towards one of the stable states, and for other states of the system, it will tend towards the other stable state. And if there's a disturbance to the system, if it's small enough that it lies within the attractor basin of the existing state, then it will just tend to come back to it, will evolve back. The disturbance will decay and disappear. But if the disturbance is large enough, it can kick the system out of that attractor basin into the attractor basin of the other state, and then it will automatically evolve towards the other state, and then there will have been a transition. But we also saw that structural changes in the system can change the sizes of the attractor basin. So you know, we used in the model that parameter C to shift the graph up and down. And so we saw that as the structural properties of the system change, the attractor basin can shrink, and then if it goes far enough, it even disappear. So as it shrinks, it becomes more likely that it can be kicked out of its attractor basin and end up at the other state. And then if it disappears altogether, it inevitably evolves towards the other state. And when we look at changes in society, we may tend to sort of focus on the obvious disturbance that caused a shift of state. when the sort of real reason may be the structural changes that caused the attractor basin to shrink. So, for example, in something like the Tunisian revolution that kicked off the Arab Spring, the sort of the trigger for that seemed to be the market trader Mohammed Bouazizi, who set himself on fire, and that sort of sparked off protests that eventually led to the downfall of the regime. So you might say that it was that dramatic and outrageous act that caused the ultimate downfall of the regime, when really it was structural changes that had happened over the preceding years that had reduced the resilience of the regime by shrinking the attractor basin of the state in which that regime could stay in power. So in fact, that's an important word, resilience. When a system is in a state with a large attractor basin, it's resilient, it will return to that state after disturbances. But if the attractor basin is small, then it has got very little resilience, and a disturbance can knock it out of that state. So with Tunisia, it was perhaps the structural changes that had occurred that had caused this loss of resilience, because in fact there had been people setting themselves on fire in protest against economic conditions and the government rule before, but it hadn't had the same effect. So it was really not that particular act, but the less visible structural changes that were the real cause of the Arab Spring. And this is important perhaps when you're thinking about things like the fall of the Roman Empire, because people love to find the cause of the fall of the Roman Empire. So it's the invasion of the barbarians, or it's climate change, something like that. But in fact, the real reason may be structural changes that had reduced the attractor basin of the Roman Empire, being in existence. And so those the things that seemingly caused it are things that really happened all the time. Barbarians had invaded before, but they were beaten back. The climate had changed before, but the farmers took it in their stride. But that's because in those days they had a large attractor basin. But when the structural changes in the Roman Empire had reduced its attractor basin to a sufficient point, it had lost its resilience, and it could easily be knocked out of that attractor basin. And then there's the idea of hysteresis, which is saying that it can be harder to get out of a situation than it is to get into it. And then there's this idea of critical slowing down, which is a kind of early warning that tells you that you're getting close to a critical transition, which is that after a disturbance, the system takes a long time to get back to normality. Now, in our model, we had just one variable, x. So we were saying that the whole of the way our society responded depended just on this one parameter x, which was something like popular resentment against the regime or something like that. But in reality, there may be several variables that contribute to the propensity for switching of the state of the system. So this is a kind of tool for thinking about it, but not necessarily a model that would apply just in this form to particular situations. We might have to introduce other variables that also behave in a similar way. So we might end up with a more complicated model. But the real point then is that when we are looking at social and historical situations where we see these kinds of things, alternate states, sudden switching, ideas of loss of resilience due to structural changes, hysteresis of it being able to be easier to move in one direction than to move back again, and also critical slowing down, so changes in the responsiveness of the system to disturbances. When we see these kinds of things in our socio-historical data, then we will be reaching for this kind of model and using that as a starting point to help us think about what's going on and develop mathematical or formal theories to explain what's going on.